Okay, hi. How are you doing today? Today we are going to talk about the need for speed. But before that, I will show the opposite of speed. Do you know what that is? Have you seen it before? Maybe added it into your code? It's always as frustrating. Even though this is red or blue or anything, it's always frustrating to have this progress bar. Because do you know what how the brain acts when it gets delays? If something is 10 seconds, then 100% of people are tired. They actually leave the room or start thinking of something else. 3 seconds, you become frustrated. Even at 3 seconds, more than half of the people leave the site. 1 second, you can experience the delay, but it's acceptable. And actually, 100 milliseconds, that is when your brain thinks that it's a direct response. But don't take my word for it. I will make a test, an experiment on you. So please don't leave. You will feel how long is 10 seconds. And I will be completely silent. I start now. What did you think?
Oh, that's painful.
10 seconds is long. It's really long. Now let's try 3 seconds. I start now. It's a little bit better, but still long. Now, 1 second. I was actually surprised the first time I saw that 1 second is also long. Did you see? It's acceptable. Now, 100 milliseconds. That was immediate, wasn't it? So when we develop applications, we need to get below 1 second. 100 milliseconds is the best, but stick to the right of this line. Actually, it's not only your brain that makes it a problem, it also will give your company less page views. Google said that they lost 20% of the traffic with only half a second delay. Amazon said that they lost 1% of sales for every 100 milliseconds delay. And people start to worry if you are doing a paying transaction, it takes too long, you will start to think that this company is not reliable, and you will tell your friends that this company is not good enough because you feel frustrated. So it's actually not only, it's also about a problem about money to the company. What we have talked about now is the web delay problem. It's what you can experience as a human being, but if you start to take other applications like IoT, AI, microservices, logistics, fintech, science, it's much more complicated. It's a lot of dependencies and thousands of calculations that need to be done, and then you make the problem much bigger. So if we go back to the 100 milliseconds and we divide this in a lot of different steps, we come down to that each step needs to be done in nanoseconds. So this is the latency requirement. And this is how you feels when you get this challenge. It's not easy, but we are here today to explain the Speedment solution to the problem. Speedment is 3 things. We developed it because we wanted to do something that could give you ultra-low latency. At the same time as we wanted to stick to Java, make it really easy to develop. And the third thing was that we wanted to stick to our existing database. We didn't want to migrate to another platform. So let's start with the ultra-low latency. And I will hand over to you, Per.
Thank you so much. When I talk about ultra-low latency, I mean we are in the nanoseconds. So maybe perhaps we are able to retrieve a stream and execute it in 200 nanoseconds or maybe 300 nanoseconds. And I'm going to tell you how short that period of time really is. But there are many solutions to do this. So I'm going to talk about some strategies that have been applied in the history before and explain why they don't work. So let's start with clusters of nodes. So let's say we have one node where I live in San Francisco and another one perhaps in New York or in Boston here. And just the sheer distance imposes a latency due to the physics of laws of physics, the speed of light. So the speed of light is kind of 15 milliseconds, but then we are in fiber, so it's 2/3 slower, and then it's back again, so it's 45 milliseconds. And we were talking about 200 nanoseconds, so this is orders of magnitude off the chart. It's too slow. But maybe if we took the other extreme and just had two Linux servers glued together with the duct tape around, and we connect them with a cable like this directly with no switches or anything, then we can come down with some tweaks to maybe 40 microseconds. And if we do busy polling and CPU affinity, we can come down to maybe 30. And if we're really an expert, maybe 25. But this is still 100 times slower than what you need, a round-trip delay. So it doesn't work. And even though, apart from that, we have to add delays from router switches. And if you are running in the cloud, then usually those networks are virtual or software networks, so they're even slower. So that doesn't work either. So let's check another solution. Maybe we can have our data in another process. But that doesn't work either, because even the inter-process communication is in the milliseconds. And if you do a context switch in your machine, you will kind of ruin your caches in your CPU and your TLB. So that will make your application slower and everything slower. So this is in the order of 1 magnitude too slow. So let's assume that we have everything as an object into memory, into the actual JVM itself. Well, then if we have much data, we will be subject to garbage collect. And if you have more than maybe 20 gigs or so, your latency will easily exceed 1 second, because if you do garbage collect, then it will exceed 1 second easily if you mutate your heap. And of course, by definition, a garbage collect will totally ruin your L1, 2, and 3 caches. They will be completely reset because the JVM will iterate over your entire memory set. So this is like 1 million times too slow. So let's talk about actual physical times. Just to read a 64-bit memory is 100 nanoseconds. And our objective is to complete a stream in 200 nanoseconds. So then we understand that we have to be really careful. Let's go back to this cable again. I think this cable is about, well, I'm about 2 meters, so it's about 3 meters. And if you take the speed of light, this means that this is maybe 10 nanoseconds here. 10 nanoseconds out of 200 nanoseconds. Just the speed of light, this is 5% of the time we have. So you understand that it's not easy to do. Okay. But of course, we have caches in the CPU. So an L3 is 20 nanoseconds, L2 is 7, and L1 is maybe half a nanosecond. And the CPU registers themselves is by definition 0. So we need to work with that kind of model instead of working with the other solutions. So let's take an overall look at a microservice architecture example. So in this example, we have some controlling entities at the top, and then they have the actual work being done with the green guys at the bottom, and they split some kind of strategy, so they use a subset of the data, each and every one, and they communicate with the high-speed bus. And then there is external communication. So in order to understand how we shall deploy this in an efficient way, we need to understand how the CPU actually works. So this is an Intel CPU, and it has 4 cores. And the cores you can see in the outer portion at the top and the bottom is the actual logic. And the further into the middle you come, you see the caches. And in the middle, the biggest area of everything is the L3 caches. And they're all shared between the CPUs, whereas the L2 and L1 is typically not shared and assigned to a particular CPU instance, core. So why not do like this? If we have our multi-service, microservice architecture Docker instances, for example, pinned down to a particular CPU, and we can view the L3 as a bus, basically. Then we can do things very efficiently. And also, if you want to do things efficiently in a CPU, you need to understand that there's a higher layer if you have several CPUs, physical CPU chips on your server. They are actually connected with a high-speed bus, creating another layer of hierarchy. So this is called a NUMA regions. So we need to understand how this works too in order to build a performance system. Okay, so the conclusion is we have to invite this guy here onto the silicon to really gain this kind of speed. So just to illustrate this, let's talk about the L1 CPU cache. It takes half a nanosecond, and that corresponds to 4 inches for the speed of light. And if you compare that to a database query that takes 1 second, now arguably it can take much less than 1 second, but it can also take a lot of more time than 1 second. So how far would the light move in 1 second, anyone? If you're thinking about astronomy, for example, how far is 1 light second? That is correct. But I want to use an analogy, so I use the distance to the moon. It's about 1 second. Not really, but almost. So the conclusion here is don't place your data on the moon. Keep it in the JVM. And now you're supposed to laugh, because this was fun. Okay, so talk about ease of development. We are using standard Java streams when we are querying, for example, a database or in memory. So we haven't came up with a known API. We stick to the one that already exists for good reasons. So I wrote an article about this in Java Magazine. I just had a back-to-back talk in the room next door, and I told the audience there about this, why we can use streams instead of SQL queries. And we can also use streams as querying in our in-memory database structure. And of course, SQL is very similar to streams. There are a remarkable resemblance between them. So count is count, limit is limit, and so on. And group by is collect grouping by, for example. So it's easy to think. When you think SQL, you can very easily understand streams, and vice versa. So let's take a look at this. In my previous presentation, I also talked about declarative constructs. So the first query there says that we want to retrieve all films with a rating equal to PG13. And that is declarative because it doesn't say how the database should do it. It's free to do it its own way. It can iterate over all the films, or it can use an index, or it can use some other kind of means, which is built in that particular database. The same is true for streams. The first row retrieves a stream that, when consumed, will contain all the films. But after the second line, another stream is created that is only containing those streams fulfilling that particular predicate. And the stream might evaluate all entities, but it might also do some other things. For example, use an in-memory index. So this is a picture showing the previous way of doing things when we mix SQL and Java. And that creates, of course, a lot of problems because they are inherently different. Whereas in the right-hand stream, we use just Java and express things with streams and functional programming, which, of course, gives a better flow. So, and the things that it's Java stream actually makes execution even faster than just being a stream itself. So let's dive into one example. In this example, we have streaming over all films and filtering out all the films that has a rating of PG13. And then we collect them using a JSON collector. And the cool thing with this stream is that even though we are reasoning about films and we are seeing, obviously we are using film objects when we express their streams, the films object never exists. And that is a little bit tricky to wrap your hand around. But this is only a notation to reason about stream or films. But they don't have to exist, and I will explain how. Because the first filter says that we can use an in-memory index. The upper table shows all the indexes. We have, by default, Speedment will index on all columns, and it's a very lightweight indexing mechanism, so it's not that expensive. So we will use the index for the rating, and we can immediately retrieve those films that satisfy that predicate. In this case, we have them at address 0 and 523. So we can go that directly, and the collector dictates that it will only retrieve certain columns. So we don't have to materialize the stream. We only have to look at that particular columns. So we never have to materialize a film. And this is important if you have 100 columns or 300 columns in a table, because then it's very costly to materialize each and every. So we haven't actually really materialized anything except for the columns we needed. And we haven't created an intermediate object because this collector here also works off heap. So it will collect all the JSON representation off heap and will not create a single intermediate object, meaning that it's very efficient and doesn't pollute your or mutate your heap. So it's fast and it's deterministic. So, and also Speedment is written very carefully so we can make use of escape analysis and allocation of objects on the heap. Have you heard about escape analysis? Anyone here? Okay, this is kind of a very hidden feature in Java. Under certain conditions, Java is able to optimize away object creation and create them on the stack if the object doesn't escape the method you're handling them within. So that's crucial for stream performance. They introspect their own pipeline, so before the stream starts, they look at their own pipeline and try to rearrange, break out, use indexes, and reorder things to get it more efficiently before the actual stream starts. We have off-heap storage and indexing, and collectors and aggregators don't create intermediate objects. And also, the snapshots in memory are immutable. So there's a first snapshot, and then after a while there's a second snapshot, but they are never mutated. And that also allows very low latency, because if you want to have mutuality, then you have to be able to handle mutual exclusion, and that is slow. So I'm going to show you a speed demo, and just in my last talk, I had this Sequila database, which is a film database. So I'm going to show you some examples here. Let me show. Can you see this? Okay. So first of all, I'm going to start, because it takes a while for this to execute. So let me first say that I don't want to use acceleration. I'll just start. Okay, now it started. So I'm going to do a JMH benchmark. JMH is a benchmarking tool that's built into the recent version of Java. And what I'm showing here on the screen are two streams. One is very simple, or relatively simple, and the other one is more complex. Now, the simple stream creates a stream that will only contain those elements that has a rating equal to PG13, like in my previous examples, and they count them. So that's quite simple, but the more complex stream is more complex, of course, thus its name. So it will create a stream of all the films sorted in length, descending order. It will skip over the first 745 films. Then it will look at the next 5 films. It will extract the get rental duration property of a film, and then we do something called summary statistics. Now, the summary statistics method is built into the Java stream interface. And this will compute things like max, minimum, and average, and count. So this is nothing that Speedment has come up with. It's a standard Java stream interface. So, and if I run this with a database, the complex, I was able to crank out 2,000 operations per second. And if I use the more simple one, it's about 5,400. So I will take this value and will paste it in here for the time being. So now let's go back and let's do in memory instead. I just change this parameter and I rerun everything again. And it will run the same tests. I haven't changed anything now in the stream. They look exactly the same. So when you're using in-memory acceleration, you don't have to change your application. You only have to have a single row saying if you want acceleration or if you don't want acceleration. So now it runs exactly the same test as before. So let's see what happens. I can already now reveal that it's going to be considerably faster. So there we are. Almost 20 million streams per second. And that's astounding. Because the average latency here would be less than 200 nanoseconds for an entire stream. Now remember, just accessing main memory was 100 nanoseconds. So I think it's quite cool. So let's fill in this value here. So that's almost 20 million, and let's take this guy and paste it in. So now you get a view of the difference, speed and difference here. And even if I would, let's take this 5,400 and write 54,000, multiply it with 10. Still, it's just a few pixels. So you understand there's a huge difference here. So that's my demo. So let's find my way back. Yeah.
So I'm just trying to understand exactly what the precipitated speed in the second example.
Yeah.
You said in-memory versus what?
In memory, the first example, I ran towards a database that was installed on my laptop here. And it was all running locally, and the database was set up standard. It was a standard MySQL database. And I ran Speedment, and Speedment rendered SQL queries, which were sent to the database and then processed in the JVM. Whereas in another example, the code was exactly the same, but instead of connecting to a database, it ran off-heap memory in memory instead. So that was the difference. Good question. Thank you. Okay, so using existing infrastructure, and I think that's now your part.
Yes, so sometimes when Per said that you need to think of how the architecture is, I guess that he means that he needed to think about it when he developed Speedment. But you, as a developer, when you use Speedment, you get this automatically. So this was just an explanation how it could be this fast. So if you have an Oracle database, or if you have Avro code or SQL Server or anything, you can stick to it and just let the application itself generate the code for you. You can deploy it anywhere. It's very good using Docker and Kubernetes. You can use it in the cloud. It works with IntelliJ, or I guess you used to use NetBeans or Eclipse.
I'm the old guy, yeah.
You can work with Spring, JBoss, or any web server integration. And it's also important to know that it's a stepwise introduction. If you have a Java project and you have a certain part of it that is slow, you can rewrite just this part. So you don't need to start all over or do a gigantic project from start. You can take this little piece and start off and just try it out. And it works from Java 8. And that's the good thing. We developed Speedment with no need to take care of Java 7. So we started off with all the good things that came with Java 8. So this is one reason why it could work so well. And when we tried it out in Java 10 now, just for fun, because we know that most of you will not have Java 10 for a long time, we were happy to see that it was much faster. But you can also use REST. It works also with the REST interface. So when is Speedment good? We often got a question about, is it possible to fit terabytes into your memory? And actually it is. You can get already now 7 terabytes as a memory, and it's not expensive. So it's a very cheap solution to just buy more RAM and get this speed. We are working with a lot of different companies. So we have, for instance, a transportation company. They had an Oracle database, and they had 6 million records in their data set. And we took them 102 seconds before Speedment, and after we could get under this magical 1 second. And the same thing with this telecom company. They have actually 5 minutes. They started it off and they went to take coffee, and then they came back, and we managed to get it down to 1 second. Healthcare industry, that was an AS400 DB2 application. They couldn't migrate to another platform, so they were sticked with this old technology, and we also managed to get below 1 second. And fintech, that's a very common use case where you need to have, there we could get down to 100 milliseconds. This is a Portfolio IQ, this application is called. And we tried it out with and without Speedment. So to try this out, on the Speedment website, you will find an initializer. And you just click in your database type, what kind of JDBC driver you want. If you want, for instance, Spring plugins or anything, you can enable the in-memory acceleration if you want to try this, or you can disable it, and you will automatically get the POM XML file that you can move into your project. So that's what we wanted to tell you today. If you want to try a license, you can just contact us, or you can, if you want to try out it on GitHub, you can just go there and do that. So do we have any questions?
So is it just an alternative version from JDBC Drive? What exactly is it?
It's using JDBC. So it's on top of JDBC, you can say. It's like, if you have heard about Hibernate. Hibernate is also ORM. So it's something similar to, or comparable to Hibernate, which is kind of converting between database, the world, and the object-oriented world. And for that, you get this treat. Any reasonable question gets a treat. How is the license model? License model is open source. It's Apache 2, and for the enterprise in-memory acceleration, it's an enterprise license model, and you can talk about Carina, because that's her department. Yeah? Okay, question is, can I filter on any column, or how many filters can I use? Is that correct?
Right, and like how optimal is it for each individual?
Okay, so you can use composite index or single index. So if you have a composite index of 2 columns, you can have 2 filters. For example, that can be applied directly using indexes, just like a database. And the solution will evaluate which index will give the best result. So if one index will give the result of 1,000 entities and another just 10, then it will apply the most aggressive filter in memory, and then apply and then use the other filters in the loop, so to speak. So it's kind of
like your own database.
Yeah, it's a kind of a query engine, you can say, that works with all the filters and knows all the indexes and knows the cost of materializing different columns and so on. Yeah. Yeah?
Perform analytical functions like,
Yeah. The question is, can you apply partition? And the answer is yes. We support partition data out of the box. So you can partition your data in, for example, integers or using any objects that partition your data, and then you have already gained a level of querying, so to speak, because then in your partition you know that that partition key all is the same, or at least is the same as the set of partition keys you have selected for that particular instance. There was a question I missed somewhere here. Okay. You too. You start. You start. Okay. Shoot.
Is there like a bootstrapping process where like the contents of your database are loaded into memory?
Yeah, good question. So the question is there a bootstrap process where you load all your data into in memory? And yes, there is. And the good thing is that this thing can happen under the hood. You don't have to care about it because it can be loaded in the background. So when you start, typically, you pull in one snapshot, but then after maybe an hour, you want to refresh your snapshot, and then you can say, I want a new snapshot, and when that is loaded into memory, perhaps a minute later, then your queries will be made against that new snapshot, and the old queries that are still working will continue with the old snapshot, because otherwise it wouldn't be consistent. And yeah.
So the database updates occur against your actual
You can do replay database updates too. But the normal thing is that you create snapshots regularly. But yes, you can also replay database. So if you have, for example, an event sourcing system or something like that, you can replay those events and update your snapshot dynamically and create a new snapshot, which is basically an old snapshot, but maybe just a few entities changed. And that is a very simple and cheap operation. So you can create 100 snapshots per second, if you want, per second. Did he get a treat? Yeah. Okay. Yeah.
What happens when there is not enough memory to fit the snapshot?
Okay, then you will have an out-of-memory exception. So you have to make sure that your data can fit. But there are ways to control how much memory do you want to allow my application to use. Maybe I don't want to allow my application to consume all my RAM because I have other applications. So there are protection mechanisms for that. But there's one requirement. You have to make sure that you fit the data you want to work with. Yes?
So I was just going to ask, the main performance boost that is achieved is through the use of streams. That's good. Thanks. The use of streams in memory.
Yeah.
Shared between all CPU.
I think there are many contributors, and which is the most contributing depends on the actual application. Of course, in terms of latency, the biggest contributor is that you already have it in memory. Because just going out in TCP back and forth will take ages compared to just accessing memory. But in terms of sheer computational power, it's more like how you handle the indexes and how you can optimize your stream. That is more important in terms of raw performance.
So in order to gain the benefit there, you have to know what to process and do all the processing on the server side without communication to a client.
Yeah, I mean, typically, if you have an application, that application also has to have a bunch of RAM because you have to be able to access your data from your application. So they're running in the same JVM, and that is maybe a bit different from other solutions where you typically have a smaller client that will do some querying, but that is prohibitive if you want to have ultra-low latency. So that's a design decision we took. Otherwise, we wouldn't be ultra-low latency. But that's a consequence of that. That is correct. Yeah? Yeah? Now it's your turn.
This might be no longer true, but there were cases, like the case of MySQL, where even if you have multiple columns indexed, it actually would not use them all.
That is correct.
And so by you optimizing with your own approach, are you circumventing that so that you actually are using all those indexes, even though MySQL isn't?
It depends. I know that MySQL isn't, super optimal in using its indices, but currently you can only have indexes of grade 2 in Speedment. So that means that you can maximum apply 2 indices at the same time. Right. If you don't use partitioning, then it's the third level. But this is something we are working with, and quite soon you will be able to use any number of filters, but then of course you must have that index in memory, and it becomes more and more space consuming if you want to have an index of 5 columns, for example, and want to have all combination of those 5s. It's going to be tricky. So I think this is a fundamental law of computer science. But it's reasonable to have maybe up to 3 or 4 indexes. But then it's going to be a combinatorial explosion of the different combinations, because you have to apply them in right order, because an index has a given order, and you can't just use something in the other order. So typically what Speedment does is that it's trying to sort predicates in an order that it already had a multi-column index on, and try to apply it in that order, and if it can, it will do. If it can't, then it just creates using a single index. Yeah?
Can you store the snapshots in the file system?
Yes and no. It's not possible in the off-the-shelf product, but we have done it in customer projects. It requires some tweaking, but it's possible to do it. So we use memory mapping in that case. We map memory to a certain file, and that file is, of course, then on an SSD drive somewhere locally. So it's possible to do it. And the good thing with that solution, too, is that if you have a microservice architecture and maybe have 3 or 4 instances of that microservice, they can share the same mapping file. So when you restart that application, even though you might have a terabyte of data, it's up and running immediately, because the operating system is managing all the paging and everything. So it's good in some cases to have that, not only from a memory perspective, but also from a system architecture perspective. Yeah?
Have you measured your in-memory solution versus databases?
Yeah. We have measured against both ordinary databases and other in-memory solutions. So, and it of course depends on the workload and the entropy of data you have. But we have seen many times, maybe a factor of 10,000 times faster than a database and 100 times faster than other solutions that are in memory, maybe nodes or using objects. But I think that we are not the best for every case. We have our sweet spot, and they have their sweet spot. So I'm not saying that we are the best in the world, but it has some good... Almost, yeah. But it has some good applications, especially in ultra-low latency.
So I'm just trying to understand the applications, and maybe I'm stuck on a client-server architecture. But if you can use the example of the financial services that you had up here before,
Yeah.
Exactly sort of what processing is going on at the server.
In this particular project we saw here with the portfolio management, we had a database with all the traders and all the papers and all the different business area, order, profit and loss and everything. And everything was pulled into memory in that particular application. And the logic was applied, and then it has a REST interface. So there was the web page calls for this REST API, and then the logic sits in the application, which has access to the in-memory graph. So that is how it worked.
And the whole thing sits in the memory.
Yeah, and everything sits on the memory. So if you would have had 2 of those, you would have to have a set of 2 snapshots.
So you're just accessing the information from the REST APIs from some client, but all the processing other than collecting or getting the data is on the server.
It's on their server side, and it's on the same JVM.
Got it.
Yeah.
Thanks.
Yeah.
Is there any replication strategy?
Yes, you can do it with file mapping is one replication strategy you can use. There are other ways to do it too. You can have one master node that will send events to participating members. So there is a cluster solution too, but it's kind of out of the scope for this presentation, but you can use some existing frameworks for that. I don't know the name of it right now, but it's in the Netflix stack. I don't remember the name of it right now, but you can use that kind of replication. Okay, more questions? No more questions, no more treats? Thank you.
Thank you.